Welcome to this colloquium of the Class of Sciences. We meet about 1 month after the previous one, and we shall meet again next week, because in our colloquia are once a month, but we leave the Wednesday free for the speaker to arrange his own or her own needs. So welcome to this colloquium, and my colleague Chiara Cappelli will give a short introduction of our guest.
Yes, thank you, Augusto, and welcome to everybody. And today the colloquium is about chemistry, and it is my pleasure to introduce our speaker, Nicola Armaroli, who comes from Bologna, where he is research director at the National Research Council, CNR. Nicola got the degree in chemistry in Bologna, then he moved to the US, and then went back to Italy. And since 1997, he works at the National Research Council, where he now runs his own group. He's a member of the Italian National Academy of Sciences and is also fellow of the Royal Society of Chemistry. His research activity is focused on photochemistry and photophysics, and with a special interest in whatever is linked to solar energy conversion, novel materials for lighting and catalysis, and stuff like this. He has published many different papers. He has a huge H index, and he's also editor of many journals, and also of the prestigious Chemistry, a European journal. Also, Nicola is a very good science communicator, and in fact, is the director of Sapere, which is the first Italian science periodical, which has been established in 1935, and for this he has written tens of editorials. He has been awarded a lot of prizes, and I hope that you will enjoy his talk today, and the title is A Glimpse into the Energy Conundrum. Okay, thank you.
I will just add one comment. We will have, as usual, some refreshments at the end, and this time they will be across the hall here, the door in front.
Good afternoon, everybody. I am very thankful to Scuola Normale Superiore for this invitation. I'm very glad and honored to be here. I was in this room maybe 20 years ago. And today I'm going to talk about energy. And I will just give a glimpse, because, you know, in 1 hour it is difficult to discuss this very complicated issue. So I am going to give you a lot of numbers. I hope not too many numbers. And I hope that you will find some of them interesting and useful for further pondering in case. And when I start these kind of lectures, which I normally start from a historical perspective. So looking back what happened in the energy domain, and this is the energy consumption in history, and for millennia, the energy consumption has been estimated to be very small. You see this red line is almost impossible to see. But then suddenly, within a few decades, less than a couple of centuries, the energy consumption went up there. And of course, there has been a big increase of this consumption. I put some numbers there, which are really impressive. Look at the electricity increase during the 20th century, okay? So the question is, can this trend last forever? Can we go upper and upper with respect to that? And we know already that the answer is no, we cannot. The reason is very simple, because we live in a bounded, finite system, which is planet Earth, and in this place, everything is constrained from very important phenomena like the growing of plants. This is the growing of the sunflower plant, which has a typical S-shaped logistic growth that you can find in many phenomena in nature, okay? But you can find it also very often in, they are phenomena showing, I'm a little bit confused with this, an exponential growth at the beginning, then there is a sort of linear point, and then the growth rate starts to decline, and then you reach a plateau. And normally you have an inflection point that for this specific phenomena is 37 days. You have similar trends, for example, for electricity. If you look at the electricity in the last 2 centuries, what one can find out is that we have, again, S-shaped type of curve, and here the inflection point seems to be already occurred in 2005. So we are in the other part of the curve. This is predictive, so we cannot be sure about that. But this is the trend that is shaping. Yeah, of course. So this is not. We cannot take this as a prediction. Okay. Yes. When we talk about energy and the ensuing climate crisis, we have a sense of urgency, as you know. We have a sense of urgency about climate, and one of the persons that is much concerned about this is the Secretary General of the United Nations. At the BBC, he released an interview last year, and he was very tough. He said, "We are careering towards the edge of the abyss. Our fate is in our hands." And this is the cover page of the Time magazine, where he was shot at the Micronesian island, which are sinking under the sea. And this is a clear message from him that we are in a hurry. The temperature trend is this one. Probably everyone here is more or less aware that 18 of the 19 warmest years since we have a record occurred after 2001. And 2016 is the hottest year on record. What is particularly worrisome is what is happening at the Arctic, because with respect to 1979, which is our reference 40 years ago, which is the maximum extent according to record of the ice in the Arctic, the area at the end of the summer in 40 years decreased 35%, which is already an impressive number, but it is much more impressive that the volume decreased by 60% on average in the last year with respect to 40 years ago. So the Arctic ice is disintegrating already. The good news is that Arctic ice doesn't bring about sea level rise because it is an ocean, okay? The problem, which is now shaping, is the melting of the Antarctica, which is a continent. So every bit of ice that melts from the Antarctica goes to the sea and contributes to the rising of the sea. And it is already established by a lot of literature that West Antarctica is losing mass, but the big trouble with this continent is East Antarctica, because the collapsing of part of this amount of ice would increase the sea level by tens of meters. So this is where the attention of scientists is focused right now. We know as chemists that the origin of this big mess is an imbalance of the carbon cycle. The carbon cycle is a complicated system in which there are 4 big reservoirs, which are the lithosphere, the ocean, the biosphere, and the atmosphere, and they exchange carbon. And they have been doing this for millions, billions of years, okay? And what you have done in the last 100 years is take a bit of this carbon out of the lithosphere and put in the atmosphere. And this has created a big imbalance, which is difficult to explain to normal people because they are not very familiar with infrared spectroscopy. So they say, why only 10 gigaton of carbon can make this big mess? There is very quantitative reason for doing so. So we are transferring 10 gigaton of carbon from under our feet to the atmosphere. About 50% of it is digested by the carbon cycle, but the other accumulates. The present annual consumption of fossil fuels is indicated there, and overall, last year, we consumed and we extracted 15 gigaton of fossil fuels altogether, which implied the release in the atmosphere of nearly 34 gigaton of carbon dioxide, which is the main, but unfortunately not the only contributor to carbon dioxide emission. We have also the change on the use of soil and others. We know that we must replace fossil fuels as soon as possible for climatic reasons and not only, but we are typically concerned about energy. We have, however, to remember that only 90% of the fossil fuel are used for energy, but there is an important bit of these fossil fuels which is used for chemical production, which is about 10%. And just to give you numbers about this, I find this Sankey diagram very instructive. You cannot see the details, but it doesn't matter. The key message here is that on your left-hand side, you have the input that we put in the chemical industry, which is 767 megaton of fossil fuels per year. And as a result, we obtain as an output 820 megatons. One can wonder why this number here is smaller than that, because we take from the environment other molecules like oxygen, nitrogen, a lot of nitrogen, like secondary reactants. So this is the balance. So when we think about our energy transition, we don't have to forget that we have to make a lot of hundreds of megatons also of chemicals that we now obtain from fossil fuels. The energy transition. So we need a transition from fossils to another era. And what's going on is indicated here. Here, actually, it is indicated what happened in the last 200 years. So, in a way, it's not correct that we are under an energy transition, because the world is always under energy transition. Because at the beginning of the 19th century, here, the main energy source was traditional biomass, and then there was the first wave of energy transition, which is the transition to coal, and then the coal left as a share of the total part of the stage to oil, and the gas then in part replaced the oil, and then there is the new transition which is coming up, which is up there with the other renewable sources. Let me emphasize that we are talking about the percentage, okay? Because of course the absolute value increased all over, as we have seen before. So there is nothing new. This always happened. But there is something new actually in this phase of the energy transition. The present energy transition is immensely complex because there are technical reasons for that. We have to change completely the paradigm, which is complicated technically. There is a global dimension. We live in a globalized world, and the energy system is a global system, and to change it is much more complicated than at the beginning of the last century. And we have, of course, accordingly social, economic, and geopolitical implications, which are very, very strong. We live in a planet with over almost 8 billion people, so it's a complicated machine to change, because energy shapes our lives every day, every second. And this will happen in a context of increasingly contended natural resources, which is another additional problem that is growing up. And the other one is climate change, which is another big problem. So I want to emphasize that this energy transition will be extremely complicated. I will emphasize this even more later on. What have we done in the last 30 years or so? You probably remember that in Rio there was an Earth Summit in 1992, where the global community first realized that we were on the wrong track and we had to change it. So what happened since 1992? What is the trend of increase of fossil fuel consumption and the other materials which are very important for our industrialized society, like ammonia, cement, or pig iron? You see the increase is absolutely huge. We have a big increase for these fossil fuels, and altogether 75% more fossil fuels burned today compared to 92. And look at these numbers. Cement is absolutely impressive, particularly due to the contribution of China. So We know since a long time what we did, but still we are in the same path because energy transition are long affairs. So we could be tempted to look ahead, as we say before, and see what will happen. Well, this is a very dangerous activity, okay? It is very risky to make prediction in general, and in energy, it is very absolutely the case. For example, this is the International Energy Agency forecast about photovoltaic growth, okay? So the trend of photovoltaic growth, the historical one, is the black line. Oh, sorry, is the black line up here, okay? The trajectory is published by the International Energy Agency in the year 2002, 10, 12, and 15 were absolutely not the real one. And we are here, and the prediction, look at the prediction in 2002 was absolutely ridiculous. So you see how it is easy to make a wrong prediction. Look at this, absolutely impressive. But there are other examples of bad forecast in chemistry. There are infamous forecasts about nuclear electricity. This is a quote from an expert in 1948. He said, "Consumption, not production, will be a problem for energy, and particularly nuclear energy." And this is another sentence said by one of the fathers of the US nuclear industry. He said, "Our children will enjoy in their homes electrical energy too cheap to meter." That's not true, we know. And finally, the greatest example of forecast, which was not absolutely exact, was the nuclear power industry remains as safe as a chocolate factory. This was written 4 weeks before the Chernobyl catastrophe in 1986. So we have to be very careful in making predictions, okay, in energy. The good news about this planet, we have many bad news, but we have also good news. This corner of the universe is just blessed with huge flows and stocks of energy. The flow of energy comes from the sun, and the stocks are most under our feet, okay? And except geothermal and tidal, basically all of the energy resources that we have a solar origin, including fossil fuels, of course, which are, let's say, fossil sunshine, and even wind and hydroelectricity is indirect solar energy, of course. Let's speak a bit on oil. Oil still remains the first energy source in this present stage of civilization. These are the proved reserves according to BP in 1998, 2008, and 2018. You see that the pie keeps on growing. I put a question mark there because these numbers are not the result of a standardized criterion that everyone follows. So basically every country, every company can declare what they want, okay? So it is not completely sure that these numbers are correct, but anyhow, at present, officially, 2018, we have about 48 years of stock of oil at the present consumption level, 48 years. And if one looks at the... This is the overall, including all the countries. So the world stock... This one, they refer to different geographical region, yes. In the Middle East is orange. This one is 48. 48. These are gigatons. These are total. These are 1,000 millions of barrels. Sorry, these are barrels. Yes, this is because you find sometimes them quoted in megatons or gigatons or millions of barrels. These are barrels, okay? Millions of barrels, billions of barrels. And if one look at what they call the URR, which are resources that have been individuated somewhere on the planet but still not extractable, we have at least 4 times as much. So the bottom line here is very simple. The world will not run out of oil and gas and coal very soon. And this is a good thing, but also a bad thing due to climate reasons, okay? We have a lot of these sources. Oil nowadays means almost nothing. This is something that the scientific the people involved in science should know. Oil nowadays is split in two categories. The first one is conventional oil, which is the one that you can get in the Middle East countries. You go to the Saudi desert, you dig a hole, and the oil comes out spontaneously, I insist, spontaneously for decades. That's easy oil. Very close to the sea, very, very easy to dispatch it. But then this easy oil is getting smaller and smaller in terms of quantities, and we are referring our attention to unconventional oil, so to extreme oil. And unconventional oil has several, there are several categories of this extreme oil, which are the tar sands in Canada, the shale oil and gas that you especially can extract nowadays in the United States by fracking, and the oil and gas in remote regions like Arctic, or the offshore and greater depths. Now they put offshore, they extract oil offshore hundreds of kilometers from the coast. That was not done, let's say, 20 years ago. So we are going in a more and more complex, from the economic and technical point of view, system about oil extraction. And things have changed because it has been estimated that in 2003, which is down here, almost all of the oil that we used was conventional. It is the blue one, but now it is almost a 50-50 between conventional and unconventional. So the situation has changed substantially. So when you go and fill up your tank, remember that statistically about 50% of what you put is unconventional. Regarding the tight shale and oil, it is the way that they do it in the US. That's a strange oil because there are huge amounts of oil and gas which are trapped in the lithosphere at about 2 kilometers deep. You dig your hole and nothing happens because the oil and gas is trapped in shale formation. And so you have to make horizontal drilling then, and then you have to make a very complicated process to crack this shale formation in order to allow the oil and gas to seep and go up. Okay, this is the fracking. And it is already established that fracking has a lot of environmental consequences and also of risks like induced seismicity related to the reinjection of the liquids. But what I want to address is another number. Due to these activities in the US right now, there are approximately 1 million oil wells, okay? US have more or less the same extraction daily as and annually with respect to Saudi Arabia. And now they have overtaken Saudi Arabia, but Saudi Arabia can extract the same amount of oil in 2,000 wells, okay? So this explains to you that it is a completely different business, even from the economic point of view, apart from the geoscience point of view, let's say. It is. It is, absolutely, it is. It is not clear at present if this whole business is sustainable. There have been a lot of companies that started the business and they were closed, and they got bankrupt and they were bought by bigger companies. So it is a situation which is at the present absolutely uncertain about the future. And we know that the bottom line with fossil fuels is that if we want to keep the track of 1.5 degrees as according to Paris, we should decrease our carbon emission right now, which are not doing. And then in 2080 we should have negative emission. We should extract carbon dioxide from the atmosphere. If we have no climate policies, as we have basically now, more or less, we will reach up to 5 degrees, and that would be absolutely a disaster, not for the Earth, which doesn't care what we do, but for human civilization, okay? We have been living, and we are living, in the golden age of energy abundance. Let me give you an example of that, an example that I experienced myself today. I came to Pisa by train and I took a Frecciarossa in Bologna. A Frecciarossa is a machine that absorbs about 9.8 megawatt from the grid, okay? And this means that instead of having a Frecciarossa, I would have had some people pedaling for me coming to Florence, okay? This would mean that I would have needed, and the other passengers, 196,000 slaves, okay? Assuming that each of them can deliver 50 watts. 50 watts is the average of an average person, not of Cristiano Ronaldo, but some of us, okay? 50 watt for 8 hours. We can deliver 50 watt for 8 hours. So this means that I could go from Bologna to Florence in just 35 minutes, because I had 430 slaves working for me, hypothetical of course, which I didn't pay 30 euro per hour, otherwise my trip would have costed a lot, you can imagine that. And we are also doing a lot of impact, and instead of making a generic example, I want to show you what is my personal impact, what has been my personal impact. That was my old car, my previous car. I bought it in 2004. It was a diesel Euro 3, and I drove it for over 200,000 kilometers. This car, during its life, drank 7.1 times its weight in terms of diesel fuel, okay? Over 13,000 liters. And this car, so myself, emitted with this car 33.5 tons of carbon dioxide, which is over 21 times its weight. So when you go out from here, you look at each car and you consider that each of them at the end of the life will emit 20 times at least of their weight in terms of carbon dioxide. Then even my grandmother can understand that it's not surprising that we are affecting the climate, you know? These are the numbers that we make. I have a new car now. It's completely different. It's electric, and it is not a car, actually. It is a battery with the wheel, because the engine is very small. It is this one, and I have a big battery. And this big battery has a material impact. And it is a lithium-ion battery, of course. The capacity is 40 kilowatt hours. It weighs over 200 kilograms. One battery, 200 kilograms, much more than your telephone battery. It is made of 24 modules with 8 cells, so 296 cells, which are pouch size, which are more or less like that, like an A4 sheet, okay? I had some hard times to understand how much material are there in my battery, because companies are not very keen to tell you what they put in their battery, in the cathode and so on. So I think that these numbers are very close to reality. In my battery, I have 10 kilograms of lithium in the cathode and in the electrolyte, 25 kilograms of nickel, 8 kilograms of manganese, 9 kilograms of cobalt, and even 48 kilograms of graphite. Okay, these are the precious material in my battery. And overall, this means exactly more or less 100 kilograms of stuff. So it's a lot of stuff, a lot of material intensity, let's say, okay? But there is a substantial difference between these two cars. I want to let you think about this. The first one was an open dissipative system, which continuously caught some fuel and emitted gas from the pipe, okay, from the tailpipe. And this one is a closed system. Yes, I have 100 kilograms of stuff, but they come with me always. I will drive, 10 years, and they come with me. They never abandon me. They stay with me. Okay. Yes, I have to recharge it, and I am arriving there. Here, coming back to my old car, you cannot control your energy provider. You cannot go to your gas station and ask to the guy, sorry, does this oil come from tar sands or the Persian Gulf or where? He doesn't know. When you have an electric car, you can control your energy provider, and you can buy nowadays energy produced only by renewables. And you can select, you go to internet, you can select providers selling only renewables. And you can do it. You have the choice, which you don't have with the first car. But most important, if you are lucky enough, you can be your energy provider. You can make the energy by yourself on your roof. And this is what I'm going to do in the future, because I'm building up a house which will do this. So I will be completely energy independent. I hope that you can appreciate that there is a difference between these two systems, okay? And then we can speak about recycling the battery, but I don't have time. But we can, maybe in the discussion, if you want, we can talk about that. In this period of the energy abundance, we have made a big aberrations. Let me show you just one. It has been established in the US that about 10% of the energy in the US are used to make food available to people across the whole value chain, okay? But it is also known that in the US, across the whole chain, about 25% of the food is wasted. So this means that 2.5% of US energy is wasted in the food that the people waste. 2.5% of US is the amount of the energy consumed by Belgium, by an entire country, okay, in 1 year. So this is an example of our energy aberrations. There are many others, but I don't have time. This one is particularly important because this is something that we can do ourselves and change our way of using the food or treating the food. There are also myths. I was contacted yesterday by a magazine that I was told that there was an interrogation at the Italian Parliament because they read an article on an English newspaper saying that the growth of renewables will have a strong impact on climate because there will be an increasing number of stations with gear switch using sulfur hexafluoride as an insulator. Well, this is true, but of course you have to count how much carbon dioxide you save using renewables. So that's something. It is completely stupid that you make an interrogation at the Parliament about this, because, for example, this is another myth I want to highlight. In Italy, nobody cares about this. Everybody is convinced that natural gas is climate friendly. In a way, it's true, because if you look at this table, when you burn coal with respect to gas, you produce twice as much carbon dioxide. Everyone knows it. But there is a problem. You have a huge infrastructure. Natural gas infrastructure is one of the greatest man-made thing in the world, okay? The gas that are burnt in Pisa and are heating this room comes from probably Siberia or Algeria, so they travel thousands of kilometers from pipelines which are that big to the pipe in your house, which is that big, and the pressure is hundreds of atmosphere, and the pressure is 1.2, and so on, okay? And across this huge infrastructure, there are leaks. And this report, recent report from the National Academy of Sciences, US, show that also the concentration of methane is increasing, and a substantial part of it is due to the leaking of the natural gas. So I told to the journalist, please ask the Parliament to make a law about controlling the leaks of the Italian gas grid, not about the SF6 in the power station, which is a much more important issue. Let's see the important points, not the details, okay? The transition to renewables has clearly started, and I'm giving you some number about this. But first, pointing out an important concept. What do we need? What do I use? What do you use every day in your life? You use two things, okay? Very simple. Electricity and fuels, that's it. This is what we need. Nowadays in Europe, in Western Europe, about 1/4 of final energy consumption is electricity, and 75%. This is exemplified also in this room. Everyone can understand that it takes more energy to heat this room, and it requires burning gas, I assume, than to lighting this room, okay? That's obvious. And these two forms of energy are complementary, because electricity is very easy to transport and very difficult to store, and the fuels is exactly the other way around. And we need both of them in a modern energy system, like it or not, okay? Now the share is imbalanced towards fuels. What about renewable electricity? With renewable electricity, we are already at an excellent level of development. So we need electricity. We can do it already very well with renewables. About over 26% of electricity in the world last year was produced by renewables. Nobody knows it. In Italy, it's almost 40%. Nobody knows it, okay? You have to tell to the people around that when they say renewables are not important, this is ridiculous, okay? At the world level, it's 26%. At the Italian level, it's almost 40%. And we pointed out this concept in an article a few years ago that the faster we go towards an electricity-powered world, the better it is. Because electrical motors are much more efficient than thermal motor, as I know as having now an electric car. So let's look at the growth of wind and photovoltaics. This is the growth of photovoltaics in terms of capacity installed. You cannot see the numbers. Let me just tell you that at the end of last year, we had almost 600 gigawatt of wind power installed in the world, and over 500 gigawatt so half a terawatt of photovoltaics. This is the installed capacity. This doesn't tell you how much electricity was made with this stuff. Now let's look at how much electricity. I spare you all the details. Just look at the yellow panel below. Last year, in wind plus photovoltaic, produced 6% of the world electricity. So they are reaching nuclear, okay, in terms of share. And they did it in 15 years. And so they produced the equivalent of 250 nuclear or coal power plants, wind plus photovoltaics, okay? So while we have been talking for 20 years with absolutely pointless discussion about the resurrection of nuclear energy, which is dead, economically dead, in the meantime, these two guys made 250, in silence, 250 nuclear power plants. And also this one nobody knows, okay? This is the production of what they made. And we can see the cost. How much does it cost? That if we look at the US, there are a lot of data available from Bloomberg New Energy. And it is already competitive in most cases in the US, already without subsidies with respect to the wind. The offshore wind, the onshore wind is already competitive. You can see it here, okay? And the onshore, it is already competitive with respect to coal. And photovoltaics is already competitive almost everywhere in the US, definitely with respect to coal. So even the economics goes in that direction. And this is clearly a consequence of what has been done. If you look last year, but the trend is in the last many years, the share of solar electricity, of solar installation, this is the 100%, the pie, the global pie of new electric installation in the world, and solar is this one and wind are the two green. So they are more than 60% alone. So it is clear where people want to put the money nowadays, not in nuclear. They want to put money here and make this kind of electricity. What we have now is silicon photovoltaics. We know that, 95%. And there are thin films that are about 5% of the world share. They are mainly in the US. So what are the competitors? Because typically people ask me, so are there new solutions? Yes and no, because if you look at the numbers, the official numbers, the organic photovoltaics has an efficiency of 11.2, official one, but in a 1 square centimeter cell. Dye-sensitized solar cell is about 12%, again 1 centimeter. You can have even bigger modules, but then the efficiency goes about 50% less. And then, of course, you have perovskite, but what they say, typically 22, 23, is again with a 1 centimeter cell, okay? If you look at bigger, it is less. And the benchmark is crystalline silicon, which is 24.4, and you don't have 1 square centimeter. You have over 13,000 square centimeters. So you understand that it's difficult to beat this guy. You know, it will take a long time to overtake this established technology. What about fuels? Well, fuels is a problem. Fuels is a big problem. Can we make fuels with sunshine? This is the other problem. We need electricity, and I showed you what we are doing, but we also need fuels. And with fuels, we can take advantage of natural photosynthesis. So we have been doing energy from agricultural crops, generation 1, like corn or agricultural waste. What is the situation nowadays of this kind of production? These are the data from BP, and to make a long story short, at present, biofuels, first and second generation, are the equivalent of 2.1% of the oil, okay? So it's a little bit of it. And it is well known that this kind of production is unsustainable from several points of view, like water use, land use, and so on. So we need progress, and we need a lot of research in this direction. We are at the ground zero almost. And here comes the project Sunrise, which is a coordination and support action, which is an action which is being funded by the European Commission. I am the leader of the work package, the scientific work package of this project. The idea initially was to fund this kind of action for a big flagship new project, like graphene and human brain, you know that. But now the European Commission decided to not fund flagships anymore, and we are in a sort of limbo. But anyhow, we are still in the work of convincing the European Commission that this is a very important domain of science to investigate on. And Sunrise include 20 partners, which are indicated here, and we are making our work to convince the European Commission, and over 200 supporters, including SNS, by the way. What is our concept? The concept is simple to say, very complicated to make. It is to use sunlight and simple and largely available molecules like carbon dioxide, nitrogen, and oxygen, and to make fuels and chemicals in order to undertake a circular approach to economy, let's say. How can we do it? How should we do it? 3 strategies we propose: electrochemical conversion, direct photochemical conversion, and biological systems. Our targets and physical constraints, we have made a lot of calculations, of course, as you can imagine. We target the production of hydrogen from water, of ammonia from nitrogen, and from sea-based chemicals, C1 particularly, and even C2 from carbon dioxide. And you have made also the calculation of the amount that we can produce in principle given specific light harvesting features and so on at different latitudes in Europe. And the scale, you cannot see it, is at the level of the hundreds of tons per hectare per year. This is our target, but it is very far away, of course, because we are starting from very small devices like that. So the idea is to go from lab devices to hectare scale pilot plants during this century. So because the transitions are very long. And now we have just published our technological roadmap. I invite you to go to our website, sunriseaction.com, download it, and please feed back to us and ask me. Just contact me in case you have something and you want to contribute. We are here. We have to push in this direction. Well, it is evident that it's time for key decisions. Key decision for, and I want to come back to my car. Let's go back to the 2 cars of before. My daily commuting. I commute 50 kilometers every day. I live in the countryside. So previously I used 32 kilowatt hour of energy to have this round trip. And to the wheels of this initial primary 32, I got only 7 with 22% efficiency, very, very small. With this car, I need only 6.5 kilowatt hours to make the same 50 kilometers, and 85% of it goes to the wheels, because the electric motor is 85% efficient. So to have the same service, now I consume 5 times less energy, 5 times less, okay? This is the real advantage of electric car, 5 times less, okay? And previously I emitted from the tailpipe 8.3 kilogram of carbon dioxide. Now I emit 0, and it is true 0 in my case because I only use renewable electricity, so the impact is very small. There is a little bit, but very small. The fuel cost before was 4.8 euro per day. Now it's 73% less. So is there anything wrong with the present energy system? This is something that our politicians should know to drive the decision, for example. But I could make other examples, but I want to stay on my personal experience. If you conceive of making an extensive electrification of the road transport, the classic question is, what about electricity demand? We can destroy the electricity system. This is not the case. And I made this simple calculation. Let us assume that every Italian is rich enough to afford to buy a Tesla Model S, the most expensive and luxurious electric car you can buy, okay? This car consumes 0.18 kilowatt-hour per kilometer. In Italy, we have 37 million cars. The mileage average is 12,000 kilometers per year. So if all the 37 million cars in Italy in 1 year were electric, how much electricity would we need? This calculation is simple. It is 80 terawatt-hours. Is it a big number or a small number? I stay on the safe side. This is a very luxurious car, so it will be less. But let's take 80, okay? It's not a big number because we already produce more than 110 terawatt-hour only by renewables in Italy. So in 20 years, which is the time frame in which you can imagine to make the transition, you can definitely work in a way in order to have, after 20 years, all the cars powered by renewable electricity. One could be surprised by this number. I was. When I made this calculation the first time, I asked 5 of my colleagues to check it because I was not sure. I said, that's too small. But what is the reason? The very reason is very simple. 97% of the times, cars are idle. They are parked somewhere, they are brutalizing our city, and that's it, you know. So that's why at the end they do not consume too much energy. And then, this is the last fraction of my talk. I want to address some of the many technical challenges and bottlenecks of the energy transition. There are many. The first one is the material challenge. Probably, at least the chemists have seen this periodic table that we, as European Chemical Society, published this year, which is the periodic table of the relative abundance of the elements. So here, each element is as big as it is its relative abundance on the Earth's crust or the atmosphere. And so there are also colors from green. The green ones are those for which we are not very concerned about availability even in the far future. But then the color gets hotter and hotter up to red, and for the red one, we are concerned that we may have supply problems even during this very century, okay? And this is something that we are trying to spread all across the schools in Europe, because it is time for students to be aware that we have problems of availability of elements, of resources. Renewable energies are material intensive. You remember my electric car. And we have this situation. On one hand, we have photons, which are extraterrestrial and overabundant input. The sun sends on the Earth the amount of energy that in 1 hour that we use in 1 year. Everyone already knows that, almost. So, but this comes from the outside. But this doesn't solve the problem at all, because we don't use solar energy as such, okay? We need to convert and accumulate solar energy. So we need materials to make converters and accumulators. And the energy system of the fossil fuels and of the renewables will be completely different for everything but one thing. In both cases, you need to dig the earth to extract resources. In the first case, you need oil and gas. In the other case, you need mineral resources to make the accumulators and the converters. And it seems that nature kind of jokes with us, because all the renewable, efficient, and even digital technology that drive all of them are based on rare elements. And let's go back to the battery of the car. So lithium, I told you that my car has 10 kilograms of lithium. So this is the Tesla battery, not my car. And I made another simple calculation. Every year in the world, there are 80 million new cars sold. So if you assume 10 kilograms per car, if all the cars sold nowadays were electric in the world, you would need every year 800,000 tons of lithium. Is it a big number or is it a small number? It's big, because nowadays, according to USGS, the lithium production is 10 times less. You certainly can increase the lithium production 10 times and even probably 50 times, but you cannot think of extracting millions and millions of tons of lithium every year for decades to come. That's not possible, obviously. Also because lithium is also needed for portable devices, like the computer we are using here, and other applications. And cobalt is even more critical, and I would love to talk about cobalt with you, but I don't have time. Another bottleneck is the energy return challenge. That's a very important concept that it is typically ignored. The concept is very simple. It takes energy to get usable energy. That's very simple. And this is quantified through the parameter ROI. What does it mean? If I go to the gas station, or you go to this gas station, the oil, the petrol that you get here, they are coming from an oil well, for sure in another continent, probably very far away, and it took a lot of energy to make it available to you next door, okay? That's obvious. And what you need to keep this civilization, this model civilization alive, is that the energy that you get out of that gasoline there is much more than the energy that you have used before, okay? Ideally, it should be 10 times more, or possibly more than 10 times, in order to have a very healthy, strongly growing economy, let's say. The ROI is the ratio between the energy that you gain and the energy required to get it, okay? The net energy instead is the difference between the two. And there is a nonlinear relationship between the two, which is here, which I reported here in this diagram as where the net energy is the percentage of the overall energy available. And what does this diagram show? Show that when you have, let's say, an ROI of 50, this means that you invest 1 unit of energy to get 50 units in return, okay? And so far we have relied on an energy system which had huge returns. Conventional oil and gas, let's say from Saudi Arabia, has ROI of tens, maybe more than 50. Hydroelectricity that was made in many cases 100 years ago, it's near 100. And this curve has a steep shape here, and a steep decrease, and there is a sort of cliff beyond which there is a strong decrease of the net energy that you get. When your ROI goes below 10, you have a steep decrease. And the good news is that the renewable electricity sources are above the solar electricity sources are above the cliff already, according to calculations nowadays, whereas many of the things we are doing, like unconventional, as you pointed out, oil and gas, they are here. In most cases, they are here. So we are making an activity which is questionable in terms of common sense, also from the economic and energetic mainly point of view. So the bad news is that the solar fuels are still here, from this part of the cliff. So we have to go up, and that's a gargantuan challenge. The other challenge, one of the other challenges, is power density challenge. We know some numbers. We know that the Earth's outer boundary, the sun sends to the Earth about 1.4 kilowatt per square meter, okay? But then there is the atmosphere, and then there is the alternation of the alternance of the night and day, and then there are the clouds, and so on and so forth. And so at the end you get 170. 170 is still a lot of energy, and it is thousands of times our need, as I told you before. So the good news is that we know exactly how much solar resources we have. It's not like oil or uranium that you go there and you try to find it. You know exactly how much you have. And that's very important. And you know where it is. The power density of renewable production is relatively small. You can produce PV or wind at the order of 1 to 15 watt per square meter, okay? So you start from 170 and then you get these numbers. And with biomass is much less, of course. And what is important to point out is that these numbers are much smaller than the numbers that we have implemented in our civilization, because in housing you need 20 to 100 watt per square meter. If you go to supermarket or offices, you have up to 400 watt per square meter. If you go to a oil refinery, you have up to 1 kilowatt per square meter. And you have totally useless buildings like this one, in which you have 6,000 kilowatt per square meter, but we can, get rid of it. We don't need it. That's another story. And but the one up are very important. And these numbers are compatible with the power density of conventional thermal and electricity generations, machines and plants like coal power plants, nuclear, and so on. So the conversion to renewables implies that, well, I will tell you later, or probably I missed the slide. Anyway, let's talk about the scale of the challenge. The scale of the challenge. It's, and let's make an example with hydrogen. Currently, we produce hydrogen in the world 70 megaton per year. Is it much, or what is it for? Well, if we assume that we produce it, all of it, by electricity, now we do it with steam reforming, through a thermal process, we get it from methane, from natural gas. In this way, moving to electricity, we would need 3.7 petawatt hour of electricity, which is a lot of electricity, because it will correspond to the 15% of the global electricity production. So producing 70 megaton of hydrogen in this way. And it would be 7-fold the present PV production, or 3-fold the present nuclear production, and so on. That would be capable of powering 50% of the global light-duty vehicles. There are 1 billion cars and light-duty vehicles in the world nowadays. With this hydrogen, you would just power 50% of it, okay? And you need a lot of electricity. So, but you don't have only cars, you have also to heat your house, you have to power your computer, and so on and so forth. So you understand that the scale of the challenge is huge. The good news is that, what about water? I'm using water for making electrolysis. The water consumption would be ridiculous, fortunately, because this would require 630 megaton of fresh water to make 70 megatons of hydrogen, which is 0.7 the current fresh water used in Europe. So water is not a problem, fortunately. On the other hand, I could wonder, would I be able to make hydrogen on my roof? So I made another assumption. Instead of having a photovoltaic panel, which is approximately 17 square meter on houses, typically in Italy, let's assume that we have a device making hydrogen. We don't have these devices. I'm making an extrapolation, let's say. How much of it? Well, I spare you the calculation with the Coulomb, whatever. Assuming one sun for a given number of hours, in 17 square meter, I would produce 80 kilograms of hydrogen per year on my hypothetical roof. Is it a big amount, or is it a small amount? Well, it's not that big, because it would be less than 20% of the natural gas methane consumed annually by an Italian family, making the thermal equivalent of hydrogen that you produce with respect to natural gas. And there is another problem, which gives you again the scale of the challenge, the time. So these devices are not existing yet, okay? You cannot go and buy them. Well, to go from the invention of the silicon photovoltaics to 0.5 terawatt that we got last year, it took 65 years, okay? So again, I hope that you have the feeling how tough is to accelerate at this level. So the energy transition is extremely complicated, and it's not going to be a very short process. So this is the slide I thought I had before. a future society powered by 100% by renewable fluxes will also entail a substantial restructuring of the space of our cities or our landscapes and in general of the urban landscape, because that will be a different world, because you have to exploit dilute fluxes of energy everywhere, but very dilute compared to present levels. We have also a disparity challenge. This is an important point. I added this slide in the train because yesterday I didn't, but I said I have to say this because this is important. It has been established, I don't have time to explain in detail why, that an ideal primary consumption nowadays for avoiding waste and giving people a very decent life is approximately 2.8 tons of oil equivalent per person. That would be, okay, primary energy. So by mid-century, we are going to be 9 billion people. So this means that by mid-century, if every human being had the level of dignity of energy, we would consume 25 gigaton of gigaton of oil equivalent. Okay, and nowadays, where are we? We are here. We consume nowadays this level, 13. Okay, and divided by the present number of people living on Earth is 7.6 billion. Is 1.8. We are at 1.8. So there is a big, not a fair distribution of energy. And let's look at some countries. China. China is the biggest consumer of energy on Earth, but still the average is below the dignity level, it's 2.2. Let's look at the Western world up there, and you see that Northern European, American countries are well above 2.8. And I spare you Qatar or Emirates, they are 20 tons of oil equivalent per year per person, okay? But clearly, the US and Canada, they have a very harsh climate, both in summer and winter, but of course, 9.6 sounds a little bit too much, okay? Europe is better, and Italy is very good. I'm sure that our politician doesn't know that. Italy is very good, it's 2.6, which is already a very good level, and in this country we shouldn't increase any energy consumption because we are excellent for this parameter. So when we are crying that because we are low in the ranking, we should show this ranking and say Italy is very a country with a very good behavior in terms of energy consumption. But let's look below. Below you have other countries, and I want you to focus on Ethiopia, 0.06. And when you see these numbers, you have to ask a question to yourself and say, what would we do with 40 times less energy? Think about your day, every day, and think about using 40 times less energy than you do. What would you do? Very easy. You'd like to get away and go somewhere else. And I think that our politicians should see these numbers because this 0.06 tells a lot of things. Just to remind you that studying energy systems allows you to understand better the world where we live. What about Europe? Since we are talking about immigration, what about Europe? I'm very close, very, very close to the end. Europe, we have a paradox. We have less than 1% of the world gas and oil resources, a bit of coal that we should phase out up to 2025, within 2025 as we promised, and you have virtually no critical materials. So when we live in this continent, and we enjoy possibly the best quality of life in the world, in Europe, in Western Europe in particular, we have to remember that our inviolable prosperity is based on energy and mineral resources coming from other continents, okay? And when we speak about immigrants, let's forget that there is also another immigration that we tend to forget, that there is an immigration of minerals, of resources that make our life enjoyable. And it comes from the same country very often from where people are coming. And we have to teach our students these concepts, you know. It is a globalized world for the exchange of people and also of goods. But we only focus on people. That's not fair, okay? And the only abundant primary energy we have in the EU is sunlight. And this is the very last number I'm going to give you. In Europe, the global mean solar irradiation is 5.5 10 to the 15 kilowatt hour per year. It's a lot of energy that sunlight bless with our continent. And our primary consumption is less than 2 orders of magnitudes less. So we use the equivalent of 0.3 of the solar input. So like it or not, we have no alternatives. We have no energy resources. We have only these energy resources, and we have to concentrate our efforts to make them available. It will be a long process, but we have to do it. So some take-home messages. The energy transition to renewables is ongoing. We know what we need exactly, electricity, fuels, and so on, and where we must go. We must go out of the fossil fuels because we are cooking our planet. We know that. We know that already. It's going to be slow and tough. I highlight it often. Energy transitions are decade-long and complex process, and this time will be even more complex. We have to teach our students that it's going to be very complex, but doable. The bad news is that time is short. The climate crisis is here. Maybe even looking outside from the window today, okay? There is no comments about that. We are in a hurry. We are in a hurry. Our politicians, decision makers must know it. We are in a hurry. We have to refrain to predict the future. We have to try to understand the complexity, which is very wide, and uncertainties, which are many. And we have to be flexible on how we will accomplish the energy transition, because maybe there will be innovation that we don't know right now. We cannot predict. So we know the path, but let's always keep open our eyes. The energy transition is not only about science and technology. It's a revolution that will affect all the aspects of human activity, like education, information, legislation, economy, finance. We have to find new financial instruments to fund this. Urban planning, resource management, international relations, etc., 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 etc. And the energy transition is a daunting challenge, but also an unprecedented opportunity. And once again, I want to invite you to motivate your students and say that their generation is the generation that have to solve this damn problem, because otherwise our civilization is in big troubles. And at the very end, someone may ask me, do you think that we will make it? Well, very honestly, ladies and gentlemen, I have no idea. But we have to try, because we have only one planet Earth, and we have no choice. We have to try. Thank you very much.
Thank you very much. And I hope that we'll have a lot of questions. And any?
At 5:30 I have the train, but we have some time. I have other slaves waiting for me.
Yeah?
I don't know, perhaps it's a stupid question, but people usually focus on not producing carbon dioxide or producing less of it. But I was thinking, once it's already produced, is it possible not to throw it out in the air, but to use it somehow, to find some use for the gas?
Okay, that's very important. You have basically two types of carbon dioxide sources. You have mobile sources, which are typically small, like cars. And it is very difficult to think that you can collect the carbon dioxide for each individual car all over the world, okay? But you have point sources, like coal power plants. And these point sources account for more or less 50% of the world emissions. So there, you can do it. But there is a problem. First, the emission from the chimney is of the order of the millions of cubic meter per hour. So you need a huge device to capture carbon dioxide, which is mixed with water vapor and all the rest. It's doable, but at that scale is, let's say, even too much. Another problem is that when you have captured it, where do you put it? The people have been working on geological sealing of carbon dioxide in the underground. And this is something not easy to do because a coal power plant is already there. And probably the underground there is not suitable for capturing carbon dioxide, for injecting carbon dioxide. So you have to put somewhere else. So you can do it in point sources, but it's difficult from the quantitative point of view and from the location point of view. Another problem is that once you find the right location underground, there are paths through which it can leak and come outside. And it has been calculated if there is some leaks, even of the order of a few percent, you might lose your advantage over time. In 100 years, it could be everything, it could be up there. So, I'm not sure if I answered to your question. Then you have to convert it. Let me say just this. You have a lot of carbon dioxide, then you have to convert it. How to convert carbon dioxide is what we target with Sunrise project. This is what we are trying to convince the European Commission, that we have to do a lot of work in this direction. So at present, the best way, since it is extremely complicated to extract, capture, and convert, is to not produce it. So that's definitely the best way. I'm not sure if I answered to your question, but he has probably something else to point out.
Yeah, I have seen many questions, so maybe you
okay,
can...
maybe you can come to me later.
Yeah.
And
So, yeah, I was wondering, what is your opinion on the relative importance of some of the renewable sources? For example, the mechanical energy sources like waves, winds. I guess if the EU were to come to you and say, we want to invest this amount of money, how would you distribute this among the various renewable sources? Would you want to diversify and kind of mitigate risk, or do you want to invest heavily in one type of source like electricity?
yeah, the other sources are available. One of the problems with wave, for example, is the power density is even smaller than the one that I showed you. So the installation should be big and should be very capital intensive. So I normally say that, okay, let's do everything. Everything possible, let's do it. But silicon photovoltaics, in my personal opinion, is a kind of miracle. You can convert with a very simple device something with over 20% efficiency. And it is extremely reliable for a very stupid reason. It has no moving parts. No moving parts in a photovoltaics. Instead, in a wave installation, you have, of course, moving parts, and they are in the salty sea. And so they are prone to, falling and so on and so forth. So photovoltaics, why I insist on that? Because it is established, it is durable, it is reliable, and most of all, you can put it on roofs, and we have already a lot of roofs, not in downtown Pisa or on the Tower of Pisa, of course, but you have plenty of industrial and commercial buildings all over the world, especially in the Western world, in China, wherever, and you must use them. You have already the platforms ready. So, to answer to your question, of course, in some locations you have like wave, tidal. You can have location where tidal is very convenient. Not certainly Italy, the Tyrrhenian and Adriatic Sea. The tides here are ridiculous. But well, there is no one solution. I think that photovoltaics is good for almost everywhere. But you need other sources, also because photovoltaics works only when you have sunlight, and waves, they work only by night, and so on. So everything but photovoltaics, in my opinion, is really the king.
Okay, so I have seen one from here, but I don't remember who was trying. Oh, no, maybe now I have another one. I have a mental list.
Thank you, Nicola, for your very nice talk. I have just a curiosity if you have any prediction regarding the good, I suppose, impact of electric car, and especially on self-driving car, which is a technology which probably soon will become available, since it may imply a reduction in the number of cars and also in the pollution and, anyway, in the West, the CO2 production of these
Absolutely.
cars. So what do you think about
at the moment, making At the moment, making prediction in this direction is not easy because it is a technology being, you know, at the very early stage. But that's true. I mean, that's another example by which we could use in a more smart way our roads in terms of space, and we can have less cars, because one of the objectives is to build up, to make less cars. Less cars. We have too many cars. 1 billion cars are too many. So in that way, if you have a self-driving car which comes to your place and it's used by everyone, because as I said, nowadays our personal car, this economic model that have been, business model that has been developed, a personal car, is nonsense if you look in retrospect, because having a device that you use for 3% of its lifetime when you have it, it's really little because it's big, you know. So absolutely, I mean, this is another possibility to reduce our impact and to use less cars, because we need to use less cars. And of course, in my personal opinion, given the problem of material availability, you can recycle it, as I said, and you can do it. My personal view is that in the future, for commuting, mass transportation will be definitely more diffused, ideally, than it is right now, even though not all of the people live in cities, but an increasing number of people lives in metropolitan areas. And, and the personal car, or maybe the shared car, or maybe the self-driving car I will use for go to the weekend and to vacations. That's my personal vision. Maybe it's wrong, because you cannot make predictions on energy, as I said, so I refrain to do it.
So I have a very naive question. In fact, you were just mentioning something about it. So you show that the amount of lithium and other materials which are used for batteries is, if every car is electric, is beyond our capabilities. But I guess that it's possible to recycle all cars and extract these materials. Is it possible? Is it?
Yes, it is. One paradox is that since it is so big, it is easy to recycle. To recycle 10 kilograms of lithium is much easier than to recycle a few nanograms of tantalum in your smartphone, for example. So it can be technically done. But if you look, there are examples of periodic table of the recycling rates of the various elements, in particular metals. And lithium is red, so it is presently recycled less than 1%. Why? Because it is more convenient to extract it virgin from Australia, from the rocks in Australia, or from the brines in the South American lakes. And here comes the legislator. Here comes the legislator. And the legislator is coming because not everyone knows. Sometimes when I say to people that they have an electric car, they look at me and say, well, your battery, when your car will be exhausted, will be thrown away somewhere. No, it's not like that. There is a regulation at the international level accepted by all countries, and of course even the European Union, which is called, looking on the internet, the extended producer responsibility. My battery, my car is a Nissan, will be in charge of Nissan at the end of the lifetime of the battery, because this is the international regulation. We cannot throw batteries in the Terra dei Fuochi, okay? That must be clear. So it can be done, it must be done, and the legislation have to adequate, and is doing that. There is a circular economy package in the European Commission, and now today the new European Commission is installed, so I hope that this procedure will continue, and Europe will continue to lead in this direction. So technically it is possible to recycle battery. There is the leader in the world is a Belgian company which is called Umicore. If you go to the website of the Umicore, they explain everything they can do for that. Nowadays it is much more rewarding to extract cobalt from the batteries, because cobalt is more expensive. So from the economic point of view, from the strict economic point of view, you can do it, and they do it already with cobalt. Lithium is not, because it's not convenient. But again, I insist, here comes the legislator. You have to do it. You must do it.
I'd like if you would say something more about ammonia production, which, as far as I know, is an old century, a century-old process, and a well-established one.
Yes. Yes, ammonia is claiming about 5% of the world primary supply for the production of ammonia. Ammonia is crucial for non-chemists for the production of fertilizers. So it's very important for us to eat, okay? It's a key chemical of our civilization. This is one I listed in my Rio slide. yes, one of the targets of Sunrise is ammonia. So we are pushing the European Commission to go in this direction and to point out that the production of ammonia from atmospheric nitrogen is a key step in the energy transition, absolutely, because we consume too much energy and we use a lot of natural gas for doing that. So that's not good, of course. And we already just submitted 2 weeks ago a big European proposal in the Sunrise Consortium on ammonia to the European Commission, and we hope it will be funded. But we are at the very beginning, so that's important, absolutely. I mean, we must make ammonia in a more intelligent way than we did so far.
Okay, so we are running out of time. Then I wish to thank Nicola again and all
Thank
of
you
you
for your
for
attention.
coming.